All right, so here's Dave, and he's going to demonstrate the aluminum torsion test, or perhaps the pencil torsion test. What's he doing here? He's using the pencil as a straight edge, and he's drawing this handy black line with the Sharpie on the torsion specimen. And you can see here again, it's the same specimen, a dog bone with the flats milled onto the ends. Now it's time to actually load a specimen into the actual chuck. For those who have your green pass, you're familiar with the spring-loaded chuck key, right? And the reason they're spring-loaded is that you can't accidentally leave the handle in the chuck, and then it starts spinning at a couple thousand RPMs, potentially killing people. This, as you'll see, does not spin at a couple thousand RPMs, closer to less than 1 RPM. But nonetheless, we have the spring-loaded chuck just to be safe. Now he's trying to get the flats, the flats on the specimen aligned with the jaws in the chuck with one hand, and with the other hand valiantly attempting to use the spring-loaded, the safety key. Now he's given up, and he's going to just use both hands to tighten that chuck, and hopefully it kind of wiggles and wobbles its way to be nicely aligned. And so he's got that in there. It looks pretty good, Dave. Yeah. Now he can tighten it all the way down. And you can see how the spring kind of pushed it out of there. So now remember that this is free to slide. And so he's got to open that side. We'll talk a little bit about why it needs to be free to slide. You can see maybe by dumb luck he came pretty close to having the flats and the jaws aligned. Maybe not quite, so it looks like he'll have to jog the torsion side, the motor side, that one right there. So he'll use that, he'll turn the right side so that the flats on the left side align with the jaws on the left side. Now keep in mind that this one does not twist. Well, it does twist a tiny bit, and that's what allows the torsion cell to read. But it's really imperceptible. Tiny fractions of a degree. I don't think it even rotates a hundredth of a degree. So effectively the left side is fixed there. The blue thing is the torsion cell. And so that jaw is fixed. Now it's important that this thing is free to slide. We do have the capability to tighten it down, but we don't. So he's just going to slide it over. It lines up right with the flats. Very good. And so now he'll use the key again on this side to tighten it down. The reason we let this thing slide is that we want to test this thing in torsion, and I know that you have all learned that torsion generates a shear stress, or torsion results in a shear stress. But as we twist this thing, imagine it's a bundle of fibers. Oftentimes we imagine even amorphous or isotropic materials to be a bundle of fibers. As we twist it, it gets shorter, and we want to allow it to shorten. And otherwise we'd impart a tensile load on it as we twist it. So it's important that that left end can slide. Okay, so he goes over here and just clicks or zeros the two channels there. You don't have to right click it. There's actually a little button for zeroing. And then he clicks play and it begins. And what's going on? This makes no sense. We've got angle and torque, right? Angle on the horizontal axis, torque on the vertical axis, but the torque is dropping. Yeah, so it turns out that with this one, as we're looking into the chuck, a counterclockwise torque is considered negative in this case, right? Not a big deal. We can handle that. And you can see this thing is rotating at, almost 1 full revolution per minute. So it's pretty high strain rate as this thing twists. And if you look down there, I can barely read that. It looks like we've hit 200 degrees of twist already in just under a minute, so that about makes sense. And we can see that it's already starting to level off. There's very high resistance to the rotation at first, and then it drops off, right? As you've learned in 303 or 306, that the torsional shear stress is not evenly distributed. It starts on the outside and it works its way inward, which means it's highest on the outside, which means the first place it starts to yield is on the outside. Okay, so now we've spun over one full rotation. You can see that black line that Dave drew on the specimen. We can see there's one full wrap of that black line now. So that black line really gives us in my opinion, a much more visual clue, or a better way to see how fast this thing is rotating and how much it's rotated. So now we're up to, I can't quite read that, for 600 degrees, 800 degrees, something like that. So we're about 2 revolutions, almost 2 revolutions, and we can see that there's almost 2 instances of the line. We're kind of making a candy cane barber pole kind of thing out of the specimen, and so we again can see right now the strain, the angle of twist seems to be pretty evenly distributed as this thing rotates. You'll learn a lot more about the relationship between shear stresses and normal stresses a little later this semester, but we wanted to show you how to use this equipment. So for those who want to use it for their project, can. Now we're just starting to see that second black line show up on the right end there, and we're approaching 800 degrees, and the torsion is very much leveled off. Now this indicates to us that all of the material is now yielding, right? Remember the torsional shear stress is highest at the surface and lowest at the center. Once the torque has totally leveled off, we can assume that all the material, all the aluminum is yielding at this point. There's 2 ways to determine the yield stress. We won't be doing it because you guys don't quite have the information you need from 303 or 306. But the first place to identify yielding is when it becomes nonlinear at about, it looks like maybe about 30 or 50 degrees of twist there. The other way to do it is by looking at once it's all yield, or what is its maximum sustained torque. And now we can see it's the shear stress, or the deformation angle of twist. It appears to be, maybe not quite as evenly distributed anymore. It looks like the lines on the right end of the specimen in the upper right corner there are kind of bunched up there. If this was a perfect world, the shear stress would be, or the twist, the angle of twist would be evenly distributed. But the fact that now it's definitely bunching up on the right end, you can see that the 2 right lines are very close together. So it's twisting more on the right end. Why is that? There might be some cracks forming. There might be some locations on the surface where we have achieved the ultimate shear stress, and it's beginning to fail. And so if I were a betting man, which I'm not, I would bet that it's going to fail on the right end, just because that's where all the deformation is starting to happen. Oh, what's going on here, Deb? Yeah, he's maybe observing that it's the right end seems to be twisting a lot more, and it's twisting more. Yeah, the universal silent movie sign for this is hot. And so, look at that. Sure enough, it fractured on the right end, and our load dropped or went up to 0, which means this has failed. So they click stop. This doesn't stop automatically like the tensile and compression methods. This would just keep going until we stop it. And now we've got to get that specimen out of there. We got a little problem. Why is he jogging it? Yeah, because there's no place to put the key. So he's got to jog that torsion head all the way around. Yeah, you still can't see it. Now he slides that thing away. It did shorten considerably. So now he can jog it. There's a high-speed jog and a low-speed jog on this thing. He's going to use the high-speed jog. Jog it around until he has access to that square keyhole. And then he'll use, of course, the spring-loaded safety key to loosen that thing up, and he can get the specimen out of there. You can see the spring there. Very important to use a spring-loaded one in the machine shop, a little less important here. So there's the short end, the proverbial short end of the stick. And you can loosen up that end. This is very interesting. If you recall the tension experiment, or at least the video of the tension experiment, the fracture surface, oh, still hot. Yep, still hot. The fracture surface was 45 degrees. In this one, the fracture surface is totally normal to the axis of the specimen, right? So it's a perpendicular, normal. And it fractured on that surface for some reason. Again, you'll learn more about that later on this semester in 303 or 306. And you'll learn much more about that when you take machine, for those of you mechanical engineers or BSEs, when you take machine component design. All right, now we got to save our data. A little quirky here. We're going to save the test data with the save icon. It's got this long file extension, mtw data, the world's longest file extension. Dave is just going to eliminate that. And he's just going to give it some informative name, online torsion data aluminum. He clicks OK. So what it has done now, it has saved the data in a proprietary ADMET format. And so he's going to go down here and save it in the 307 folder. There it is. Okay, but now he needs to export it, right? We're not too interested in proprietary file formats, so we're going to export it as a comma-separated variable. He's going to put that somewhere intelligent. Looks like on the desktop in the 307 folder. It's always fun for me to look at this folder because it's kind of a little tour of TAs past, right? There's some legendary TAs on this list here. But Dave is now first making his mark, so he makes his own folder. He's going to export the comma-separated variable file into there. So now we have it in something that we can read with MATLAB or Ease or Excel, Google Sheets, whatever. It takes a little while to do. Not quite enough time to play the girl from Ipanema here. But okay, so it's done. I'm saving. Dave, being the cautious and conservative engineer that he is, he's going to open up the desktop and just make sure that that data file looks the way it should. Double click on that. Okay, so now you can see that there's a time, a torque, and an angle channel that all show up, and then a bunch of other stuff that says NaN, N-A-N. That's kind of mathematical speak for, or computational numerics speaks for not a number. Thank you, Dave.